Welcome to Unit 7 on Cartesian Vectors, and that is the title of Lesson 7.1 as well. Before we dig in, what are Cartesian vectors? We want to be reminded of what we've already done in vectors, and in Unit 6, Chapter 6, we talked about geometric vectors. So now we're jumping from geometric vectors to Cartesian vectors. Well, what's a geometric vector? Geometric vector was any vector that you could draw on a two-dimensional plane. So you notice I can move this particular vector left, right, up, down, diagonally, all around, but what I can't do is bring it up off of the flat surface or push it down into the flat surface. What I also can't indicate is whether or not a vector is actually coming left, right, up, down, as well as up toward the camera, say. So what Cartesian vectors allows us to do is express vectors or discuss vectors based on the Cartesian grid. Cartesian grid, typically, we're used to it looking like this with our x-axis and our y-axis. But now what we're actually going to be able to do is we're going to be able to add a third dimension, because in the real world, when we're talking about real world applications of vectors and magnitude and direction, you can move left, right, backward, forward, and up and down. And so we need to be able to come up off of the plane of this page, and a third dimension indicated by a z-axis, which has a positive direction, and a negative direction, just like the rest of these. And actually often the negative direction is indicated by a dotted line for each of them. And so now we have a three-dimensional space with positive and negative directions for each of them. We're not going to get into that until lesson 7.4, I believe. But we are going to right away get into plotting things on a Cartesian grid in two-dimensional space and learning some other tools and strategies for working with vectors and problem solving on a Cartesian plane. So again, let's consider from Unit 6, we could have taken any geometric vector, vector u, but now in Unit 7, we're going to be expressing vectors as Cartesian vectors. Okay, so I'm going to draw essentially, it's not quite the same, but let's say that's vector u again down here, and this time it's been drawn on a Cartesian grid, which makes it a Cartesian vector. It has a tail at Q and a head at R. Now QR, the vector QR, is a Cartesian vector because its endpoints, Q and R, can be defined using a coordinate pair. Okay, it's somewhere, Q is somewhere here, x1, y1, and R is somewhere here, x2, y2. Their position can be described using coordinates. That makes this a Cartesian vector. Now, what we can do with this vector is we can translate it, we can shift it, move it, so that its tail is at the origin. Now, that makes it a lot easier to talk about this vector. So I'm going to go ahead, I'm not measuring, but I should be measuring the exact length and get the exact direction. But I'm going to move this vector over here. This is now the position vector u. Okay, it's a special vector, it's still a Cartesian vector, but it's been translated so that its tail is at the origin, O, not Q, sorry, O, and its head ends up being at point P, which is represented by the coordinates A, B. So we're talking in general terms here. I have some Cartesian vector that has been translated to give us the position vector. And this position vector, still same as equal to vector u, is now also called by its coordinates with square brackets. Okay? So the distance between the length of QR is the same as the length of OP. And I'm just going to label some of the things that we have here. We have a Cartesian vector right here. And then this vector right here is the position vector. The position vector. So we use square brackets to distinguish the name of this vector from the point that it ends at would be rounded brackets, the coordinates a, b. And this has the same magnitude and direction as the vector OP. Now, what you also may be able to see already is that we can resolve any given vector on the Cartesian plane into its rectangular components, where we have a horizontal vector, which corresponds, it's vector A, has the same, it's represented by the x value in the point P, and we have vector B, which corresponds to the y-coordinate of point P. Okay, and now what's interesting about these is they become the rectangular components of point P, so now we can see how we're already being able to build the vector OP, or the vector U, or the vector AB from its horizontal and vertical component vectors. And that brings up another piece of language that we need to be able to use, because A and B, as they are the horizontal and the vertical, they are actually built from something called unit vectors. It's just a smaller diagram here. We have our x-axis and our y-axis, x, y. And a unit vector is a special vector that become the building blocks for any Cartesian vector. They always have, well, it's a unit vector, so it always has a magnitude of 1. And they're special vectors that have their tails at the origin. So if I draw a vector along the x-axis, and it has a magnitude of 1. This is called vector I. Vector I is the horizontal unit vector. The vertical vector, positive direction, with a magnitude of 1 unit is called vector J. Okay? Again, these both have a magnitude of 1. I is horizontal, J is vertical, and scalar multiples of these vectors can be used to build any vector, any Cartesian vector, in as a position vector. Okay. The notation for Cartesian vectors here, these unit vectors, we would represent I equals square bracket 1, 0. And we would represent J as being equal to the vector 0, 1. This indicates that the magnitude of I is 1 in the horizontal direction, and the magnitude of J is 1 in the vertical direction. And again, these vectors can be used to express any other Cartesian vector as a basic building block. So for instance, if we resolved P into its horizontal A and its horizontal B, then we would express A as a scalar multiple of I. So maybe A is, 2I. And we would express B as a scalar multiple of J. Maybe it's, 4 times J would get us B. So then the vector U, or the vector OP, would be 4J plus 2I. And that would get us from the origin to point P. But we'll get into that in more detail as we move along. So we'll note that we did over here, we did unit vectors. And now we're just going to relate this diagram to these diagrams with a couple of other notes, okay? We have already established that the vector U here, U, is equal to A times I. So let's say A was, 2 units along the x-axis, then the vector A would be 2I. But whatever it is, this length is the value of A times the value of, the value of A times vector I. So this is AI plus, where I is a vector, plus B times J, B, J. Okay? Also, from this, we can gain some other things. So we've used AI here. Well, what is AI? AI, it's a scalar multiple of the unit vector I, is equal to the vector A0, sorry, because we know that it is only in the horizontal direction, and A is going to be the multiplier by which you multiply the unit vector. Anything times 1 is itself. So the length, the magnitude, or actually not just the magnitude is represented by A, but the vector itself is A0. And the same goes true for the vector bj. The unit vector j is being multiplied by a scalar coefficient of b. That's going to give us the vector 0, b. It's going to be a vertical vector with a magnitude of b. Now these things become pretty important as we work together in proofs, okay? So what else can we say then about the vector u? Well, we can express it in another way. We can express it using this type of language. If u is ai plus bj, then u is a0, the vector, plus the vector 0b. So what we've established then, if u can be expressed as the vector ab, and it's any vector in the Cartesian plane, then any vector in the Cartesian plane can be expressed as the sum of a horizontal vector and a vertical vector, its vector components. So putting some of this stuff together, you can kind of already see how we're going to be doing our calculations. We're going to be able to get the magnitude of any vector because it's simply going to create a right angle triangle at the origin, where we're going to be using Pythagorean Theorem, a squared plus b squared equals c squared. That's going to get us the magnitude of any vector on a Cartesian plane. And then just briefly, before we get into an example, what happens then if we're going to be adding Cartesian vectors? Adding vectors. Well, here we only have one vector, but we said that we could express it as a horizontal vector and the sum of a horizontal vector and a vertical vector. Well, if we have two vectors then that we need to add together, all we need to do is express the first one in terms of its rectangular components, in terms of its horizontal vector and its vertical vector. And we can take the second one and break it into its horizontal and vertical components. And then all of a sudden, all we need to do is add the horizontal components of vector 1 to the horizontal component of vector 2, and add the vertical component of vector 1 to the vertical component of vector 2. And when we put that all together, we end up with the single new vector, the sum of these two vectors. Well, what about multiplying a Cartesian vector? Well, again, we can think of it in terms of, we can think of a single vector in terms of its horizontal and its vertical components. And if we wanted to multiply this vector, and it would be heading then in this direction, and you could multiply it by a fraction or by a whole number, all you're doing is thinking about the horizontal component vector, and you're going to be able to multiply that and think about the vertical component vector. Sorry, it look more like that. And then you're going to multiply that. And they look like this and this. So if I wanted, for instance, 3u, all I would need to do is take 3 times its horizontal component and 3 times its vertical component. Really what I'd be doing is taking 3 times a0 plus 0b, and then distributing my scalar multiple of 3 to both of those vectors, and that would work out to give me my component vector, in which I would also then be able to distribute. It's again a bit messy here. You'll see it better in an example. I can distribute this 3 to the a to give me 3a, and I give this times the b to get 3b. 3 times 0 is 0, 3 times 0 is 0. So you can see what we end up with in this case. If we did 3u, we would end up with the vector 3a, 0 plus 0, 3b. And then we could put that together, and that would be the vector 3a, comma 3b. How do we subtract vectors? Well, just like Unit 6, we talked about subtracting a vector is the same as adding its negative, or adding its opposite. So we'll get into that as well. Okay, example 1, we're going to be playing with these Cartesian vectors and all the different operations that we can use. We are given vector A. Vector A is the vector 5, negative 7. And we're given vector B. Vector B is the vector 2, 3. Now these are given as position vectors, so their tail is at the origin, their head is at 5, negative 7 for A, and vector B, its tail is at the origin, its head is at the point 2, 3. We need to determine each of the following. There are going to be 7 of these coming our way, starting quite simple and then getting a little more complicated. So we need to express A in terms of its horizontal and vertical components. All right. Well, if I know it's represented by the vector 5, negative 7, then horizontal is going to correspond to the x value, and vertical, its vertical component is going to correspond to the y value. So that's pretty straightforward. All I have to say is that vector A is equal to the sum of, so maybe I'll just draw it out here so you can see what's happening first. It's going to be the sum of two vectors, where one of them is the horizontal vector. That's going to have a horizontal displacement of 5 and a vertical displacement of 0. And the vertical vector, which is not going to move horizontally, it's going to go up or down the y-axis. It's going to go down 7, negative 7 in the vertical direction. And that's all that's asking us to do. Take A, split it into its horizontal and vertical components. Let's look for B. B says, express vector B in terms of unit vector I and unit vector j. So just getting us used to different language here. Since B is the vector 2, 3, well, I can see that I have a magnitude of 2 in the horizontal direction. So that's going to be 2 times vector I plus 3 in the vertical direction. That's going to be 3 times the unit vector j. And that's done. There's an expression of vector B using the unit vectors I and j. Looking at C. C says, calculate 3a. Well, for 3a, I'm just going to take my scalar multiplier of 3. I'm going to take my position vector A, which is 5, negative 7. And at this point, I'm just going to distribute the 3 to both of these, my horizontal magnitude and my vertical magnitude or displacement. So this is what it looks like. We've got, inside our bracket, we've got 3 times 5 is our horizontal displacement now, 3 times the horizontal displacement, and 3 times the vertical displacement, which we can simplify as 15, comma, negative 21. Moving along, D. So what have we done? We've expressed A in terms of horizontal and vertical components. We've expressed B using the unit vectors. And now we've done a multiple of position vector A. Now we're going to do the sum of A plus B, position vector A plus position vector B. So all we need to do here is take these two position vectors 5, negative 7, plus 2, 3. And we're going to split them into their horizontal and vertical components. So if A moves horizontally 5 and B moves horizontally 2, then my horizontal component for the sum of A plus B is going to be 5 plus 2. My vertical component is going to be negative 7 plus 3. And when I simplify that, I get the vector 7, negative 4. Scroll that up. So you have a bit of a glare there, you can't even see it. And a few more here. I'll move across the page here. We'll do E over here. In E, we are going to use position vectors A and B to get a new vector, which is 2A minus 4B. So a couple things going on here. Each vector has a scalar multiplier, and again, I mean, it's the same as working with integers. It's the same as algebra. We're going to use bedmass. You're going to do multiplication before addition and subtraction. Okay, I can't go 2 minus 4 and then I have negative 2ab. That doesn't make any sense. So what we're going to do first is we're going to simply write down that we have 2 times vector A. And we're going to subtract 4 times vector B. Okay, just simply write what is there. Sub in your position vector coordinates for vector A and your position vector coordinates for vector B. And now you can see that we're going to deal with each of these independently still, because multiplication has to happen before addition and subtraction. So I have 2 times the horizontal displacement for A and 2 times the vertical displacement for A. That's going to give me the vector 10, negative 14. We're going to be subtracting the vector 8, 12. Okay, now from here, we are going to simply use this subtraction for, we are going to have the horizontal displacement of 2A minus the horizontal displacement of 4B. So our new vector is 10 minus 8, that's its horizontal displacement. Its vertical displacement is negative 14 minus 12. And now we can simplify. We've got 10 minus 8 is 2. Negative 14 minus 12 is negative 26. Okay, step by step, go carefully. You're not reinventing the wheel. You're just using different language, really. Language of vectors, Cartesian vectors. Okay, let's look at K, A, B, C, D, E, F. No, F. And actually, I'm going to have to erase and make some space for F. Okay, F is a little bit trickier. F says that we're going to basically take our vector that we're given. Vector A is the one we're going to be talking about. And we want to find a vector that is collinear, which means it lies right on top of vector A, but only has a magnitude of 1. So it's a vector with a magnitude of 1 going the same direction as vector A. Okay, let's write that down. We need a vector collinear to A, or collinear with A. It's called Ka. So we're going to be able to take A, multiply it by some scalar, depending on the length of the magnitude of A, then K is, in this case, I can see it's going to be a fraction, okay? And that's going to scale down vector A in order to have a magnitude of 1 unit, okay? So we're told K comes from the set of real numbers, and our goal is to find K so that Ka has a magnitude of 1. So they could have also written that as just this, right? The absolute value of Ka equals 1. That's our goal. All right, so that's our first step, is we're essentially saying that we want this absolute value of Ka, its magnitude, and we're going to basically just rewrite that same way we have been. So we're looking at the absolute value of scalar k times the vector a, which is 5, -7. So we're finding out which value of k is going to give this a magnitude of 1. Well, let's keep on working this through. I'm going to distribute k to my horizontal component. And we're always talking in terms of, right now we're talking in terms of magnitude, so I need the absolute value. So I've got k times 5, and the vertical component is k -7, or could better write that as -7k, and this guy as 5k. That makes it a little easier to work with. And we know that that is going to equal 1. Okay? So now we're thinking, well, how do I make this true? How do I determine what the magnitude of this is? Well, remember, you have its horizontal component and you have its vertical component. In this case, the vertical component is downward. But basically, what we are trying to find then is the length of this right here. And then we're going to find k that's going to be able to scale it down to have a unit length, a length of 1 unit. Okay, that's what we're doing here, so that you can visualize it. So again, we're going to be using then Pythagorean Theorem. So we've got a, and I'm not going to use a and b, I'm going to use x and y because we already have a and b in here. So that's the horizontal component and the vertical component. And we know that if we take x squared plus y squared and square root it, we're going to get the magnitude of our hypotenuse here, the length of our hypotenuse. So that's what we're going to be doing. I'm going to take the square root of the square of 5k. We're going to add the square of -7k. And when we do this work, we end up, the square applies to the numerical value and the variable. So here we have 25k squared, and here we have -7 squared is +49, k squared plus 49k squared. We can add those up because they are like terms. 25 plus 49 is 74. 74k squared. I'm just going to take this 1 down in every step, because at this step I'm going to square root both sides. Well, the left side's not going to change. Square root of 1 is 1. The right side, now I just have 74k squared, and I'm going to solve for k. That's our goal, right? So I'm going to divide both sides by 74. So on the left side, 1 over 74 equals k squared. And I'm going to swap sides here as I solve for k and take the square root of both sides. Remember, the square root can be a positive or a negative. 1 over radical 74 as an exact value. So thus, the two unit vectors that are collinear with vector A are going to be 5 times our scalar quantity k in the positive direction, and 5 times our vector in the vertical direction of -7, or negative our scalar times each of those. So let's say that, let's write that. So 2, therefore, 2 unit vectors. So now we don't have unit vectors in just the horizontal or vertical direction. We have a unit vector going collinear, 2 unit vectors collinear with A are, our first one is going to be 5k, right? Because here's our vectors. This is what we're looking at, right? So we're looking at the vector 5k. So, and positive, we're going to use the positive values first. 5 over radical 74, comma negative 7 over radical 74. And using our negative value for k, we get negative 5 over radical 74, comma, positive 7 over radical 74. And we can easily double check that each of these vectors has a magnitude of 1. We would just put them into a right angle triangle, which they are. We have a horizontal of 5 over radical 74, and we have a vertical of negative 7 over radical 74. And if we were to calculate this, okay, we should get 1 unit. And how would we do that? Well, a squared plus b squared equals c squared. Okay? Same thing here. You do the same thing. You're going negative 5 over radical 74, and you're going up 7 over 74, radical 74, and you'd calculate that. And if you get 1, then you're good to go. Okay? That's a way to double check it. Quick walkthrough of what we did. We needed a vector, some vector that was 1 unit in length, but it was going the same direction as A. So it's some scalar multiple of vector A. We distributed k to the horizontal component and the vertical component. Then we used a Pythagorean theorem in order to simplify and combine our k's and solve for k and square root both sides. We ended up with k squared equals 1 over 74. We knew that when we took the square root of that, we were going to end up with a positive value and a negative value, which gave us 2 possible unit vectors that were collinear with A. I mean, if A is going, in this case, A is, A might look something like that. Okay, so the 2 unit vectors that are collinear are of 1 unit and of 1 unit. And that's what we have here. In G, we're asked to get the absolute value of vector A minus vector B. So this means we know we're just talking about the magnitude. Our final answer is only going to be a magnitude where direction is not important, okay? So what are we going to do here? Well, we have the magnitude of A minus B. So we're going to take the horizontal components, 5, and then we're going to subtract the horizontal component of b. So here first we have the vector, where the horizontal component is 5 minus 2. The vertical component is negative 7 minus 3. We're going to simplify that. That gives us that we're looking for the magnitude of the vector 3, negative 10. Okay? To get the magnitude of that vector, we're just looking at, so again, we could picture it. We're going 3 to the right and then 10 down. So we're looking for this, essentially the resultant of the horizontal component vector 3, magnitude of 3, and a magnitude of 10. Okay, we don't care if it's positive or negative. It's not going to matter. It's going to come out in the wash. So what we're looking at then is the square root of application of Pythagorean theorem. We've got 3 squared plus negative 10 squared. That's going to give us 9 plus 100, which is our final answer. The magnitude of the difference vector A minus B is the square root of 109, radical 109. It might be worthwhile to pause here and try a couple of the easier practice problems. And you might say, well, that's all great, but what if I get a vector that is expressed at 2 different points using 2 points on the Cartesian grid that are not at the origin? So it's not a position vector. So it might look something like this, where we have our y-axis and our x-axis, and we have the origin, 0, 0, and we have the point P, or P1, represented by the coordinates x1, y1. And then maybe over here you have P2 represented by the coordinates x2, y2. And we want to be able to determine the magnitude of, or the vector that can be used to represent, the vector P1, P2. So what we're actually then looking for is the vector P1, P2. Well, we have enough knowledge about vectors already to know that if we want to go from P1 to P2, that we can break this into two vectors, and we can actually say that P1, P2 is the vector PO plus the vector OP. Okay, how would we write that? Well, P1, P2 as a vector is equal to the vector P1O plus the vector, OP2. Now, we can think about this another way. If we want to talk about our vectors both as going as the position vector, so for instance, this one is already given as a position vector. It's got its tail at O and its head at P2. If I wanted to express this portion of it, I'd have to take its opposite. So I'm actually going to start with O, P2, and we are going to subtract the vector OP1, because that's adding its opposite. Or sorry, adding a vector is the same as subtracting its opposite. It'd be like taking a double negative. It's taking the vector backwards, but then subtracting it, okay? And now what that allowed me to do is express both as position vectors, which allows me to express both of them in terms of their coordinates. So OP2 then could be represented as the vector x2, y2, and OP1 is going to be the vector x2, y2. In which case, we can finish the difference here by taking the horizontal component of each. Sorry, I wrote, these should be 1s, x1, y1. Then all we have to do is take the horizontal component, x2 minus x1, and the vertical component, y2 minus y1. And this is then the vector P1, P2 is simply the difference between the second horizontal coordinate minus the first horizontal coordinate, the difference between the two. And the y direction here is the y magnitude displacement. The vertical displacement is the difference between the second and the first. Which allows us to get this right angle triangle, which leads us to talking about the magnitude. So the magnitude, I'm not even going to do that. I'm just going to take P1, P2 vector absolute value. That tells us we're dealing with the magnitude of P1, P2, which is a vector in any place on the Cartesian grid, not represented as a position vector. And all we need to do then is take the square root of its horizontal displacement plus the square of its vertical displacement. And so again, here you really just have the distance formula. Okay, let's put that into play. In example 2, I'll leave these notes up there as long as I can. Example 2, find the coordinates and the magnitude of Cartesian vectors between 2 points. In A, we're going to find the coordinates and the magnitude. So coordinates, and magnitude. There's going to be 3 of them. In A, we're taking vector AB, where A is at the point 1, 3, and B is at the point 7, 2. All right, so the coordinates and magnitude of the vector AB. So AB is going to be the vector, and I'm just really copying from up here, right? I'm going to take all my x's is going to be x2 minus x1, and my y is going to be y2 minus y1. So 7 minus 1, and our vertical is 2 minus 3, 2 minus 3. Now in this case, it really does matter so sometimes we would say if you're doing a distance formula, like up here for magnitude, it doesn't really matter which one you call point 1 and point 2, point A and point B, as long as you're consistent. But if we're looking for the coordinates of vector AB, direction and magnitude both matter. It's going to matter that you're taking bx minus ax and then by minus ay, okay? Or yb minus ya is probably how I should say it. At any rate, simplify this, we get the vector 6, negative 1. That is the vector AB. That's the coordinates of vector AB as a position vector. Now to get its magnitude, the magnitude of AB is simply square root of 6 squared plus negative 1 squared. This is 36 plus 1 is 37. This is going to be radical 37. Done. B. CD for point C at negative 10, 0, and point D at 0, 10. All right, so we have a horizontal vector and a vertical vector. It's already kind of broken up into those components, and we're going to be calculating its coordinates. So again, we're taking the difference of the horizontal displacements. So we've got 0 minus negative 10. And the difference of the vertical displacement is going to be 10 minus 0. It's going to give us the vector 10, 10. And for the magnitude of CD, then we're just taking the square root of 10 squared plus 10 squared, which is the square root of 200. And that's done. All right, let's see it one more time. In C, we've got vector EF, which is a vector anywhere on the Cartesian plane. It's defined by the point E, which is 4, negative 3, and the point F, which is 1, negative 7. And we're going to follow the exact same steps here. The coordinates of position vector for EF are, again, x2 minus x1, comma, y2 minus y1. Be careful with your brackets, etc., and your positives and negatives. We've got 1 minus 4 is negative 3. Negative 7 plus 3 is negative 4. And now for the magnitude, I already know this is going to end up being a 3, 4, 5 right angle triangle. So 3 squared plus 4 squared, 9 plus 16, the square, that's 25, square root of that is 5, okay? 3, 4, 5 right angle triangle, where the position vector, the magnitude of the position vector EF corresponds to the hypotenuse of this right angle triangle. Okay, how do we write a geometric vector in Cartesian form so that we can do some trigonometry and algebra with it? and represent it using Cartesian language. Well, in Unit 6, we talked about vectors, geometric vectors, and we found out that we could split them, just like Cartesian vectors, into a horizontal component and a vertical component. And then we needed to talk about the magnitude of the horizontal component and the magnitude of the vertical component. Well, let's reflect back to this lovely shape here, which is your unit circle. Now, when we drew anything in a unit circle, so let's say I have this vector, it's in my unit circle, okay, which means it has a magnitude of 1, okay? Now that means that its horizontal displacement is the cosine of theta, where theta is the angle that we make in standard position, okay? So the distance here would be cos of theta, and the length here would then be the sine of theta, because we can kind of make that right angle triangle there, or has the height of sine theta. That's because this point in the unit circle is, the x-coordinate is cosine of theta, and the y-coordinate is the sine of theta, where theta is the angle that our ray or our vector makes with the positive x-axis. Now, let's translate this over here. We're not in a unit circle, okay? If we were, it might look something like that. So the magnitude of our vector is not necessarily 1, okay? Which means that the horizontal rectangular component, the horizontal component of our vector is not necessarily cosine of theta, but it is some multiple of the cosine of theta, okay? So in this diagram, then, and what is that multiple? Well, the multiple is v. The scalar multiple is v, because instead of being a unit vector of 1, it's a vector of length v, which has a magnitude of v times 1. So what does that mean? That means that down here, instead of just having the x displacement, the horizontal displacement, being represented by the cosine of angle theta, where this is angle theta, it's now going to be the magnitude of v times the cosine of theta. Okay, that is the horizontal component. Well, what's the vertical component? The vertical component, right here, is the absolute value of v, the magnitude of v, times the sine of theta. Okay, so that tells us that the vector v here, while it was any geometric vector with value v, that the vector v as a Cartesian vector is equal to the absolute value of v, its coordinates are the absolute value of v times the cosine of theta, and its y-coordinate is the absolute value of v times the sine of theta. Let's apply this in example 3. Example 3, we have forces as Cartesian vectors. Okay, so in Unit 6, we were kind of saying, okay, a weight is hanging, or a car hits another car, those kinds of things. Now we're going to be putting those ideas into a Cartesian form. So what are we told in this example? We're told that we're going to write a force of 200 newtons at 20 degrees to the horizontal in Cartesian form. All right. I mean, a quick diagram might help us out here. But basically, we have the horizontal, okay, and we have 200 newtons at an angle of 20 degrees to the horizontal. So we've got a vector that's coming from here, we've got 20 degrees in there, that's theta, and we have a force of 200 newtons. And what we're really asking then is, how do I express it as the combination of my horizontal displacement and vertical, I shouldn't say displacement, force, okay? Horizontal force and vertical force, the sum of those two things. So here we go. This is vector F, and vector F then, right here, right, is the absolute value of F times the cosine of 20 degrees, and its y coordinate is the absolute value of F, the magnitude of F, times the sine of 20 degrees. Simplify. We know, so I already plugged in my theta. If I'm doing the general term here first, I could write theta there and theta there. So now I know that the magnitude of vector F is 200. So I'm looking at 200 times the cos of 20 degrees, and my y coordinate is going to be 200 times the sine of 20 degrees. Plug those two in my calculator separately. I will get the coordinates of vector F are 187.9, and the y coordinate is 68.4. Okay? Example 4 puts this geometric into Cartesian form type work into a more complicated word problem. We have a ship and the current. So first, some information about our ship. Its course is set to travel 23 kilometers per hour relative to the water on a heading of 40 degrees. The current that the ship is working with or through or against is on a heading, it is 8 kilometers per hour. 8 kilometers per hour. And it is on a bearing of 160 degrees. And that is from 160 degrees. And the ship says it's a heading of 40 degrees. Okay, what are we going to do first? First, step 1, write each as a Cartesian vector. Cartesian should have a capital C. Well, headings and bearings are measured clockwise from north, right? Okay, so that's what we're looking at, which is equivalent to clockwise from the positive y-axis. So these have to be converted into angles with respect to the positive x-axis. Okay, that'll make sense once I draw it. I'm going to take this ship, so we'll deal with the ship first. Ship. And we're on a Cartesian plane here. We've got our x-axis and our y-axis. Y is north. And we have a heading of 40 degrees, and that's always from north. Okay? So this angle right here, 40 degrees. That tells us that angle theta with respect to the positive x-axis is 50 degrees. Okay? 50 degrees. Now, using what we know, that means that the ship vector is going to be equal to the velocity of the ship times the cosine of theta and the sine of theta. So we have the velocity of the ship, which is 23 kilometers per hour, times the cosine of theta, which is 50 degrees, and the y displacement, is going to be 23 times the sine of 50 degrees. Just plugging in what we did in the notes just previous to this. So a ship traveling on a heading of 40 degrees clockwise from the positive y-axis. That's the same as 50 degrees from the positive x-axis. And then we're going to let s represent the velocity of the ship. So the velocity of the ship is expressed right here. Okay, that's the vector that represents the velocity of our ship. Now, the current. The current is flowing from 160 degrees. All right. So if we think about this from the north, we're going 160 degrees. That's 20 degrees shy of 180. And we're coming from that direction, okay? So this is the current coming from that direction. Well, the current doesn't stop, so we can represent that also in standard position, because that's what we need to do. We need to represent this in standard position from the positive x-axis, okay? Well, that is equivalent to, let's just think about this geometrically. If this is 20 degrees, then its opposite angle is 20 degrees. So this blue angle here then is 90 plus 20. That's going to be 110 degrees, okay? So this red one was 160 degrees, coming from a bearing of 160 degrees. That's equivalent to, from the positive x-axis, an angle of 110 degrees. And why do we need to do that? Well, we need to do that because we need to express vector c with respect to the positive x-axis in order to get its velocity. So the velocity of the current then, we know the magnitude of this vector c, I can make space right here, vector c is equal to the magnitude, which is 8 kilometers per hour. The horizontal component then is 8 times the cosine of 110 degrees. And the vertical displacement, or the vertical component, is 8 times the sine of 110 degrees. Good. That's part A. We've written each geometric vector as a Cartesian vector. And now we head into part B, which says, determine the resultant velocity of the ship. Determine the resultant velocity of the ship. Okay, so we've been given how the ship is moving with respect to the water, and we've been given the water's effect on anything in the water. So to put them together would be to get the resultant velocity of the ship. So we're going to let r represent, let the vector r be the resultant. Nothing new there. And that tells us then that the vector r is going to be equal to the velocity of the ship plus the velocity of the current. So what are we doing here? Well, let's take our two vectors that we've already expressed. We have the vector s, which is 23 cos 50, comma 23 sine 50. And we're going to add vector c, which is 8 cos 110, comma 8 sine 110. And now in order to get the resultant, I need to add the horizontal components and then the vertical components. So here's our vector. It's 23 cos 50 plus 8 cos 110, comma 23 sine 50 degrees plus 8 sine of 110. And now carefully plug these in your calculator, and you will come out with approximately, for a horizontal velocity, horizontal component, 12.048, and a vertical component of 25.137. Okay, now this is the coordinates of the resultant vector r in standard position. Okay, but we're not done. We still need to find the magnitude of the resultant. Okay, so the magnitude of the resultant is the absolute value. That's thinking about this as a right angle triangle. It's going to be the square root of 12.048 squared plus 25.137 squared. That is going to come out as approximately 27.875. Okay, so we have the ship with respect to the water traveling at 23 kilometers per hour, certain direction. We have the current from a different direction at a speed of 8 kilometers per hour, and they're somewhat working together. They have a speed together. The ship has a speed of, with the current helping it out, has a speed of 27.875 kilometers per hour, but we still don't have its direction. We still don't have its direction. We want to express its direction as a bearing. So what we're going to think about, we're just going to take this coordinates that we found. I'm going to put it in a little diagram for us. Okay, here's north, or y. Here's x, and the resultant is at 1225-ish. So let's just say 1225. Okay, that's really a terrible drawing. Let's at least do it a little bit to scale. 1225. It's a bit better. There's our resultant. 12.048, comma 25.137. And in order to express this as a bearing, we need an angle relative to north. So we're looking for this angle. We'll call it angle beta. Okay? And for angle beta, we have the two legs. It's a right angle triangle, right? So we have the two legs. We have the, this would translate to being up here. So we have the opposite and we have the adjacent. Okay, so in order to determine what angle beta is in this right angle triangle, we're going to take the tangent of beta is equal to opposite over adjacent. So opposite is our x value, which is here, 12.048, over our adjacent, which is 25.137. To find the angle B, I take the inverse sine of both sides, and I end up with approximately 25.6 degrees. So the ship then is traveling at a velocity of 27.87 kilometers per hour at a bearing of 25.6. Okay, so the resultant velocity of the ship. Therefore, the ship's velocity is 27.9 kilometers per hour at a bearing of 25.6 degrees. Dun, dun, dun. What did we do? Oh, we took two vectors and we converted them into Cartesian vectors. Boom, boom, vector S and vector C. And we found the resultant, just like we would have before, by taking the horizontal component of each and adding the two vertical components of each, simplified into the coordinate vector here, representing vector r, the resultant. Then we found the magnitude of that and the angle that it made relative to north in order to get its velocity of approximately 28 kilometers at approximately 26 degrees of north. Okay, practice problems, practice problems, practice problems come from page 367. You're responsible to know how to do numbers 1 through 18. Thanks for watching.